All right, good afternoon. How is everyone?
Doing good, Nick. How are you doing?
Doing okay, thanks. All right, let's start with any questions, either homework questions or questions on what we've talked about so far, or anything else really. Well, that's good that you made it to class. Sorry you caught a cold. I'm kind of figuring I might get lucky and skip the usual fall colds this year because I'm not like around anybody. So, how rigorous does proving have to be on the homework? So induction proofs are generally very rigorous. Um, Most of the homework questions are not, about pie fights or horses, but they're about, relationships of mathematical expressions and such. So those should be fairly rigorous. Now, you can always say algebra when you're taking something and expanding a polynomial expression or factoring or things like that. Um, as long as you're doing reasonable steps and you're not skipping a million steps at once, you can just put down algebra for an explanation of that. But if you move from one step to another, there should always be a clear um, reason why that next step follows from what was written above. If you want, feel free to send me an example that you're not sure of the rigor on, and I'll be happy to look at it and say, you should add more detail here, or this is fine, or something like that. But I'll ask you to do that, today, or early tomorrow at the latest, rather than Thursday night, because that's too late to do it. Oh, and you slept through 224, and we went over the final exam ahead of time and gave all the answers, so that's too bad you missed it. But oh well. All right, other questions? Yeah, maybe it was recorded. We'll see. All right, let's talk about Towers of Hanoi. This is kind of our last induction example, but this is a classic problem to talk about in this subject. And the first time I taught this, I was getting ready to go into school in the morning. This was several years ago, and I needed some props, and so I went to the recycle area and pulled out some old pizza boxes and cut out some cardboard circles of different sizes and used that. And at the end of the school year, one of my students who was graduating um, came to me with a present and said, this is for you. And it was a cool little official version of Towers of Hanoi. It was made out of like wood, and it was all polished and very professional looking. And I used that for this lecture normally, except it's locked in my office at Clark, and I haven't been able to get it. So we are back to whatever props I could find, which is the top of my pepper shaker, a chili container, jar, and my Quaker Oats container. So slightly better than cut out cardboard box tops from pizza boxes, but we'll make do with this. All right. So what is Towers of Hanoi? Towers of Hanoi is a really old game. And the basic setup is you have a series of 3 sticks sticking out of the ground, and you have discs, and these discs have holes in the middle, and so you can take a disc and you can slide it down. These poles coming out of the ground, and the discs have different sizes, and you begin with a series of discs sitting on one pole with the largest disc on the bottom. All right. So I'm gonna play this with 3 discs. So there's my big disc, there's my medium, and there's my small. Okay. And the idea is you start off with these stacked in one position, and your goal is to move this pile of discs from one place to another. Okay. Actually, let me use these because they're smaller. So there's my pile of sticks, and let's mark off 3 positions. So there's one, there's another, and there's a third. All right, and you have to move these discs according to a very simple set of rules. First rule is you can only move one disc at a time. So one disc at a time. You can only take from the top. So I can't move this chili sauce cover directly. I can only move the pepper container that's sitting on top. So you can only take from the top of a pile. And you can only put a disc on an empty pole or a larger disc. So for example, I could take this and I could put it on that because that's an empty spot. I can take this, I'm not allowed to put it here because it's bigger than that, but I could put it on an empty spot. And now this disc I could put either here because that disc below it is bigger, or I could put it here because that disc is bigger. I could take this disc and move it back here. This disc can't go anywhere because it's bigger than, you know, all of the other discs. But if I had something like this, right, I'd be free to move that disc over there if I wanted. So you move one disc at a time, you only take from the top, and you can only put down on top of a larger disc or a totally empty pole. And the goal of the game is to start with, you know, all of your discs in one pile like this and try to move it to another pole. All right, so how do we do this with 3 discs? So normally I have somebody come up and try to do this in front of the class. And if I had a cat, I would let the cat do it now, but I don't have a cat. So I'm just going to do this for you. So I don't know, I'll just, you know, move that there and move this here and move this here and plunk that over there. And this will go there, and this will go there, and this goes there, and we're done. And we moved all the discs from one spot to another. Okay. Now how did I do that? Well, I've done this before, right? So I kind of know, you know, the general procedure for moving 3 discs. And how many moves did that take? It took 3 moves. Sorry, 3 discs. It took 7 moves. Right? So what were the 7 moves? 1, 2, 3, 4, 5, 6, 7. Now, if I had started with only 2 discs, how many moves would it take? 1, 2, 3. And if I was playing this game with only 1 disc, how many moves does it take to move that pile to another pole? It takes 1. So yeah, we love finding formulas and patterns, right? And for n discs, as someone suggested in chat, this looks like 2 to the n minus 1. And we'd like to know if that's actually accurate. Is that always how many moves it takes to move n discs in Tower of Hanoi? Well, it is. And let's prove that with mathematical induction. So let P of n be the proposition it takes 2 to the n minus 1 moves to move n disks in Towers of Hanoi. All right, kind of an odd sounding proposition, but that's okay. We can assert that there's a truth value to this statement. It's a declarative statement, it's a proposition. All right, one sec. So there's a story that goes with this game, which is that there's a cave, and there are monks that live in this cave and play this game nonstop, day and night. And the game is played with 64 jade discs, so very beautiful, very expensive Tower of Hanoi game, 64 discs. And at the beginning of time, all 64 discs were sitting on one of these sticks. And these monks labor day and night moving the discs from one stick to another, according to these rules, with the goal of moving all 64 discs to another stick. And the legend is that this marks the life of the universe. And when the last disc is moved to this other stick, the universe will end. And so, for whatever reason, this is what these monks are doing. And so 64 of these discs would, if this formula is correct, take 2 to the 64th minus 1 moves. So how big is that? 2 to the 64th minus 1. Well, it's that many moves that would be required. And let's suppose these monks are really fast, right? They've got super monk skills, and they can move 100 discs per second. It's going to take that many seconds for the universe to end. And if we take that many seconds and divide it by 3,600, that's the number of hours. And if you take that and divide it by 24, that's the number of days. And if you take that and divide it by 365, that's the number of years. So 100, 1,000, 10,000, 100,000. 100 million, so 5.8 billion years. So we're past that if you believe 13 billion years for the age of the universe. But that's 100 discs per second, so this takes a really long time, okay? This is something we'll get into a lot next quarter when we look at efficiency of algorithms. 2 to the 64th is huge, right? It's a big number. 2 to the 10th is 1,000. 2 to the 20th is 1,000,000. So we go up about 3 orders of magnitude for every decade. So this is about 10 to the 18th. Big numbers. All right, so let's prove this proposition. Well, how are we going to prove a proposition about playing a game? We want to prove that if we have n discs, it takes 2 to the n minus 1. Okay, so to do this using mathematical induction, first we need a base case. Is P of 1 true? Well, P of 1 says it takes 1 move. Boom, there you go. There's a demonstration of it. If you start on this pole and you need to get there, there's 1 move. There's 3 starting poles for each one. There's 2 possible destinations, and I can illustrate in each case I can get there in 1 move. So P of 1 is absolutely true. So the inductive step prove that P of n implies P of n plus 1. So let's suppose that for n disks it takes 2 to the n minus 1 moves. Well, let me play with 4 disks now. And I want to move these 4 disks from here over to there. I'm going to have to put one of my poles up here because my oatmeal container's too big. So we want to move 4 disks, okay? There's a really easy way to do this. Let's say I want to move these 4 disks from here to here. I already know how to move 3 disks. We already did that, right? And if I ignore my oatmeal container cap, the largest disk, and I only play my game with these top 3 disks, it's exactly the same game as just having 3 disks. Because each of these is smaller than this, which means if this is the only disk on a pole, it's as good as an empty pole. I can always move a piece onto here. So to move all 4 disks, here's what I have to do. First, I do whatever moves I make to move these 3 disks up here. And then I move that to my destination. And then I do whatever moves I need to move these 3 disks over to here. And I'm done. Alright, want to see me do that again? I'll move this pile over to here. First I'm going to move these 3 disks up here. And then I'll move my biggest disk to the destination. And then I'll move these 3 disks over to there. And we're done. So what does that look like in a proof? How many moves do I need to move n disks? Well, I need to move n minus 1 disks to an empty pole, and then I need to move my biggest disk where I'm trying to get to, and then I have to move these same n minus 1 disks to that destination pole. So number of moves, so let f of n equal number of moves for n disks. So the number of moves for n plus 1 disks is simply the number of moves to move the first n disks, the n smallest disks, plus 1 move to move the biggest disk, and then another f of n moves to move that stack of smaller disks on top of that big one. Alright, well, if we know that f of n is equal to 2 to the n minus 1, why? Because p of n is true, right? That's our hypothesis. Since we're assuming p of n is true, the number of moves to move n disks is 2 to the n minus 1. Therefore, the number of moves to move n plus 1 is 2 to the n minus 1 plus 1 plus 2 to the n minus 1, which is equal to 2 to the n minus 1 plus 1 minus 1 is minus 1 plus 2 to the n, which is 2 times 2 to the n minus 1, which is 2 to the n plus 1 minus 1. So a really simple demonstration. The number of moves that it takes to move n plus 1 disks is 2 to the n plus 1 minus 1. Well, that's what p of n plus 1 says. Therefore, p of n implies p of n plus 1 for all n bigger than or equal to 1. Therefore, p of n for all n bigger than or equal to 1 by mathematical induction. So that is a valid formula. It doesn't just happen to work in a few cases. We've proven with mathematical induction that this works for all numbers of disks bigger than or equal to 1. Alright, so that's proven something that we probably didn't know we were interested in proving. The number of moves required to complete Towers of Hanoi. But buried within that proof is also an algorithm. There's a solution to playing this game inside that proof. So suppose, you're locked down in COVID, and you can't go out and do stuff, and so you're trying to figure out things to do. So you decide to play Towers of Hanoi, right? And you've got two other people in your household, and you want to play Towers of Hanoi with 5 discs, right? If you can convince one of your friends to solve the 4-disc version, you can solve the 5-disc version without any effort, right? You just go to your most bored friend and say, hey, do this 4-disc Tower of Hanoi game for me, right? And I've got 5 discs. I'll go with a CD for my 5th disc, right? I want to move all 5 of these discs, okay? What am I going to do? I'm going to go to my friend and I'm going to say, hey, can you solve, the 4-disc problem for me? And they'll show me how to do that, right? And I'll end up with a disc over there. And then I'll take my biggest disc and I'll put it here and I'll say, hey, do that again. Can you put those 4 discs over here? And they'll go through their process and do that. And I just solved the 5-disc version. And now if another friend comes to me and says, I want to do the 6-disc version, can you solve a 5-disc for me? I'll say, sure. I know how to solve a 5-disc. I just did it, right? I just have to get my friend to do the 4-disc version. But the actual work I have to do is minimal, right? All I got to do is say, move 4 discs, and then I do one actual disc move myself. I put that there, and then someone comes along and moves that. Yeah, this is a CD a really good friend made for me. It's a cool mix of deep cuts from early bands. All right, so we can code this without too much sophistication. So let's look at this. Yeah, and your friend contracts out the 3 discs, and somebody else contracts out the 2 discs. And, all this contracting out has to end at some point. Well, where does it end? When somebody comes to you and says, hey, I'll give you $10 if you can move this disc to that pole. And you say, sure, and you don't have to split that $10 with anyone. You just go boink, and you're done. Yeah, CDs are awesome, right? You can get external drives pretty availably, or when we get back to in-person life, right? You can always grab a CD player inside one of the PCs in the collaboratorium. You can read your discs from there. Tape recorders are harder. I actually have a reel-to-reel tape recording of the Apollo 11 moon landing and the first steps on the moon that my dad made in '69 while I was watching it with him. And I have it on magnetic reel-to-reel tape. So I'll have to burn that to a disc sometime. Cassette and VHS, yeah. Anybody ever do 8-track tapes? Woo! 8-tracks were cool because you never had to rewind them. They just keep going and going. All right, let's look at code that that will solve Towers of Hanoi using this idea of hiring subcontractors to do your work for you. And yeah, this is exactly recursion. So I wrote this in C, and C is kind of goofy with arguments, because to pass integers you need to pass pointers and stuff like that. So I don't want you to get bogged down on the C syntax here. Actually, we don't need to change these things, so this one's not bad. All right, so I'm going to write a tower code which takes 4 arguments. It takes the number of disks you want to move, and then the pole you want to move from and to, and I'm also going to tell it which pole is unused. So when I call tower 8, 1, 2, 3, it says I want to move 8 disks from position 1 to position 2, and I'm just telling the code position 3 is unused. Okay, we can do that in code, but I'm trying to make this simple. All right, so what does our Tower of Hanoi code look like? This is the whole thing, right? There's no real intelligence in here. I'm keeping track of the number of moves, so I have a global variable, aka an evil global, that I increment each time I call tower. That's just for accounting purposes. So if the number of disks you want to move is 1, I just call my move function and say, let's just move from the from disk to the to disk. Okay, first disk to second. Because there's no work to do. Just pick up the disk, move it from the source pole to the destination one. Otherwise, what do we do? Well, it's 3 steps. Take num-1 disks, move them from the from pole to the open pole, and then move 1 disk from the from pole to the destination, and then move num-1 disks from that open pole that you moved them to up here to the destination disk. All right? That's exactly the algorithm that we just used to play this game on paper with my physical disks, right? So move n-1 disks, and then move your biggest disk, and then move those n-1 disks again. And this is where I'm asking a friend, hey, can you give me a solution to this problem? Can you give me a solution to that problem? And the only work I actually do is moving from the biggest disk from the source to the target. All right, and this is recursion because I don't have a friend to help me do this. I put on a different hat and I say, I'm the 3-disk solver person, you know, and I solve the 3-disk problem. And how do I do that? Well, I put on my other hat and I say, I solve 2-disk problems, and I solve the 2-disk problem, right, and give that to my 3-disk problem solver person. And when I'm done moving the 3 disks, I go back to myself and I say, hey, my friend solved my 3-disk problem. I move the 4th disk. And then I repeat the whole thing again to move those first 3 disks. All right, my move function is just a print. I'm just going to print out, you know, the from pole and the to pole, and every 5 lines I'll just print out a new line. So this is the whole guts of the code. And this is corresponding to the inductive step, right? This corresponds to this notion of you know, move n-1 disks. We're looking at n+1. So if we're looking at n+1, move n disks, move 1 disk, move n disks, right? Well, we're looking at moving n instead of n+1. So it's move n-1, 1, and n-1. And this, that's our base case, p of 1. Now, if we didn't have this, we would eventually get down to having to move 1 disk, and that would end up trying to move 0 disks, and then trying to move -1 disks and -2 disks, and we get into nonsense and end up with a seg fault at some point. So we have a base case which stops all of this recursion and basically says, oh, but if you have to move just 1 disk, just move it, right? There's nothing stopping you. All right, so if we run this, towers, all right, there's a solution for 8 disks. And it tells us the total number of calls was 255. All right, so let's do this for 3 disks. All right, there's our solution for 3 disks. So let's go back to our polls and see what this is saying. So I'm going to label these 1, 2, and 3. And so we're going to read left to right and then top to bottom. So start off, we're going to move from disk 1. We're going to move from pole 1 to pole 2. That's this. And then we're going to move from 1 to 3. And then we're going to move from 2 to 3. And then 1 to 2. And then 3 to 1. and then 3 to 2, and then 1 to 2, and we're done. And if we do the 4-disk problem, I don't think I have the wherewithal to do this. 1 to 3, 1 to 2, 3 to 2, 1 to 3, 2 to 1, 2 to 3, 1 to 3. So at this point we've moved our first pile, and then we put 1 to 2, so 2 is up here. And then we do the same process, 3 to 2, 3 to 1, 2 to 1, 3 to 2, 1 to 3, 1 to 2, and 3 to 2. And there we go. So if you want to do this for 64 disks, there's your solution. And if you follow each of these steps, you will eventually move all 64 disks. And there goes the universe. Of course, it's going to take 2 to the 64th minus 1 divided by 5 lines of output to get to this. But there's no deep thought involved in what those steps should be. But what's going on inside the computer, that's a whole different matter. There's actually not all that terribly deep memory going on either. If you know the language of recursion, our stack never gets terribly deep, right? 64 levels at the most. Yeah, it does kind of look matrixy almost. I need to throw in more different characters so you can see it scroll. Alright, so that's Towers of Hanoi, and it's another example of using mathematical induction to prove something and having that be kind of a parallel to an actual algorithm we can implement to craft a solution to something. All right, so let me end our discussion of induction with one more concept, which is useful to know. This is something called strong induction. So our regular induction or weak induction works like this. If we're given P of 1 and we're given that P of n implies P of n plus 1, then we can conclude P of n for all n bigger than or equal to 1. Right? So we need a base case, and we need to know if you can get to the nth step, you can get to the n plus first step. That's our regular induction. Strong induction is easier to satisfy sometimes. Strong induction is the following theorem. Given P of 1, given P of 2, given P of 3, and so on all the way up to P of n, and given let me do this differently. Given P of 1, given a base case, and then given the following statement, P of 1 and P of 2 and everything up to P of n, if all of that implies P of n plus 1, then we can conclude P of n for all n bigger than or equal to 1. Okay, the difference is in this inductive step. In regular induction, we have to show that P of n gets you P of n plus 1. With strong induction, we only have to show that given all of these propositions, we can get to P of n plus 1. Now certainly if we can show that P of n gets you P of n plus 1, we can show this, right? Because if all of these things are true, P of n is also true. And if we know P of n gets you n plus 1, then certainly this gets you n plus 1. But this is sometimes easier to show, right? Because we don't have to rely just on P of n to get here. We can also take as given P of n minus 1, n minus 2, all of these other values of P. So this is an easier hypothesis to satisfy sometimes. Or put it this way, this hypothesis gives us more stuff to work with in proving P of n plus 1. Okay, so it's a stronger hypothesis in some sense. And why does this work? Well, because we know if P of 1 is true and this statement is true, then we know that P of 1 gets us P of 2. And so now we know P of 1 and P of 2 are true, and this will get us P of 3. So now we know 1, 2, and 3 are true, and so this will get us P of 4, and so on. And so we can, chain rule n times to get P of n for any n. But this is a useful form. And sometimes there's things that are much easier to prove with strong induction than with regular induction. So let's do one example. So let P of n be the proposition. N can be written as a product of primes. And I'm going to say one or more primes, because if n itself is prime, we're going to, say that, 7 equals 7. Well, this is a product of one prime. It's just 7 itself. We're going to count that as legal. So P of n is the proposition that n can be written as a product of primes. In other words, there is a way to factor it. We're not saying it's unique. We're just saying there is a way to write it as a product of numbers that are only prime. Okay? And we want to prove P of n for all n bigger than or equal to 2. Okay, well, base case, let's just pick on P of 2. P of 2 says 2 can be written as a product of primes. Well, 2 is a prime number. And so we can write 2 as, just 2. So P of 2 is true. So we've got a base case. Okay, let's use strong induction here. Let's prove P of 1 and P of 2 and all the way up to P of n implies P of n plus 1. And this is for n bigger than or equal to 2. Well, this is actually pretty easy. So there's two cases. Case 1, n plus 1 might be prime. If n plus 1 is prime, we can write it as a product of primes. We can just write it as, n plus 1. So this is trivially true. Okay, so if n plus 1 is prime, P of n plus 1 is true. So the more interesting case is n plus 1 is not prime. Okay, we know that if a number is not prime, it means it has a factor between 1 and the number itself. So there exists some factor f bigger than 1 and less than n plus 1 such that f divides n plus 1. Well, this means n plus 1 equals f times k, where k is an integer. That's what divisibility means. And we also know something about k. We know k is not equal to 1, because if it was, n plus 1 would be f, and n plus 1 is bigger than f. And we also know k is not equal to n plus 1. Because if it was, n plus 1 would be f times k, f would be equal to 1, and we know f is bigger than 1. So, just as f is between 1 and n plus 1, k is also between 1 and n plus 1. And we're basically done. And we're done because we've stated n plus 1 can be written as f times k. Well, f is a number between 1 and n plus 1. And p of f tells us f can be written as a product of primes. And k is a number between 1 and n plus 1. And p of k tells us k can be written as a product of primes. So n plus 1 is a product of primes times a product of primes. And that tells us p of n plus 1 is true. But this boils down to the fact that we need to know more than just p of n, right? We're using this strong inductive hypothesis which says that every number smaller than n plus 1 can be written as a product of primes. Well, if n plus 1 is composite, just take any two numbers that multiply to give you this and write each of those as a product of primes. And we can do that because that's our inductive hypothesis. Every number smaller than n plus 1 can be written as a product of primes. So that's kind of a classic application of strong induction. Now, uniqueness of factoring, that's a whole nother ball of wax. That's a pretty hard thing to prove. All right, that's pretty much it for induction. You got homework questions to work on, and you're welcome to ask questions about those now or office or Friday. But any questions at this point? Did anybody stay up all night watching election returns? I stayed up for a while, and then my girlfriend and I switched gears and watched other stuff instead, because can only watch so much of that. But I've been watching *Halt and Catch Fire*, which some students recommended about a year ago, and that's a fun series on Netflix. Early days of personal computing industry, interesting stuff. All right, so let's go on. So next unit is counting. 1, 2, 3. We're done. We know how to count, right? It turns out that, like a lot of things in this subject, something that we have a pretty good intuitive understanding about actually is a gateway to a lot of deeper concepts. Just like set theory can lead us into a discussion of incompleteness and paradoxes and so on, counting can lead us into all kinds of interesting areas in permutation and statistics, and all sorts of other things. And we'll loop back into things like Fibonacci series and good stuff like that. So we're going to play with counting. And we're going to start by looking at the number of ways to do things. So if you want to do something like order lunch, or choose people to go on a trip, or arrange people in a picture, right? We can ask how many different ways are there to do that. So number of ways to do something. And I want to talk about some rules we can use for calculating these numbers of ways to do things. So the first thing is the product rule. And this will be fairly obvious sounding, but it turns out to be useful. So given some procedure, so some procedure that you want to do, like I say, ordering lunch or choosing people to play on a basketball team or whatever. Given some procedure which can be done, which can be performed as a succession of two tasks, T1, T2. So let me name this procedure P. So given a procedure P which can be performed as a succession of two tasks, T1 and T2, we can ask how many ways are there to do this procedure. So if T1 can be done N1 ways, and if T2 can be done N2 ways, then P can be done, guess what, N1 times N2 ways. That's the product rule. So you've got some way to do a procedure as a succession of two tasks. First task 1 followed by task 2. And the succession is important here. And if you can do task 1 N1 ways and task 2 N2 ways, then the whole procedure can be done a total of N1 times N2 ways. Okay, that's our product rule. And the whole trick with the product rule is figuring out how to apply it to different situations. So for example, given 2 students and 20 desks, how many ways can students sit down? How many ways can they choose which desks they're going to sit at? So you got 20 desks in the room, you've got 2 students, let's say they're taking a makeup exam, and you're going to assign them seats. How many different ways can you assign them seats? And we can solve this with the product rule by thinking of this task, this procedure of assigning 2 students to 2 of 20 desks. We can think of that as a pair of tasks that we're going to perform one after the other. So let T1 be the task of assigning student 1 to a desk. And let T2 be the task of assigning student 2. To a desk. So the first thing to be sure of is that performing T1 followed by T2 will result in performing your desired procedure. Well, you know, this will put a student at a desk. This will put the other student at a desk. That's really all there is to it. Right? So if I do T1 and then I do T2, I've accomplished my goal. And there's no assignment of these 2 students to desks that can't be accomplished with these 2 steps by doing T1 first and then T2. The order is irrelevant. All right. So that takes a little bit of thought to make sure that you're not just kind of, making some assumptions here. But yeah, this procedure of assigning 2 students to, out of 20 desks, T1 followed by T2. So now how many ways can we do T1? So T1 can be done, so how many ways? Toss it up in chat. Trying to assign a student to a desk. 20 possible ways, right? Because we haven't done T2 yet. We've got an empty room, we got 1 student, got to choose which desk they're at. T1 can be done 20 ways. So N1 equals 20. Okay, here's where the succession comes in. We've already done T1, which means 1 student is sitting at a desk, and we're not allowed to have students share a desk. So how many ways can student 2 be assigned to a desk? Right, there's 19 desks left. They can sit at any of those 19. So this can be done 19 ways, so N2 is 19. And so according to the product rule, the total number of ways to sit 2 students and in a room with 20 desks is 20 times 19, that's 380. Alright, that's all there is to the product rule. It's never more complex than that. But we can do a lot of interesting things with this. Alright, so product rule examples. Let's keep going. So, student IDs. So let's suppose that your student ID is a combination of 2 letters followed by 1 digit. Alright, we want to know how many possible student IDs are there. Well, that's a rephrasing of the question, how many ways can we assign a student ID to someone? So how many ways can we construct a student ID? Well, we can break the process of constructing a student ID into a series of tasks. Task T1, choose the first letter. Task T2, choose the second letter. Task T3, choose the digit. Right? The procedure of creating a student ID is a simple succession of these 3 tasks. How many ways can we choose the first letter of a student ID? Well, there's 26 letters, so there's 26 ways. How many ways can we choose the second letter? If there's no restrictions, 26 ways. How many ways can we choose a digit? There's 10 digits. So 26 squared times 10, that's the number of student IDs. Is it 6,760? Good. Cool, thank you. That's all there is to it. Alright, let's go back to one of our favorite 250 topics. How many 4-bit strings are there? How many 4-bit numbers can we construct? A bit is a 1 or a 0. How many 4-bit strings are there? Well, the procedure of creating a 4-bit string is a succession of 4 tasks. Task 1, pick bit 0, task 2, pick bit 1, task 3, pick bit 2 in task 4, pick bit 3, where, you know, I'm labeling my bits bit 0, bit 1, bit 2, bit 3. If I perform these 4 tasks, I will end up with a 4-bit number. And any 4-bit number I can get by performing these 4 tasks in a particular way. So the total number of 4-bit strings is exactly the same as the number of ways I can do these 4 tasks in succession. Well, how many ways can I pick the value of bit 0? I can pick a 0 or a 1. There's 2 ways to do that. How many ways can I pick bit 1, bit 2, and bit 3? 2 ways each. So the total number of 2-bit strings is 2 times 2 times 2 times 2, which is 2 to the 4th, which is 16. And so there's another way of seeing the fact that there are 16 unique 4-bit numbers. And if I had done this n times, let's call it m, right? The number of m-bit strings would have been 2 to the m. And so this is something that we encounter in Engineering 250. If you have an 8-bit number, there's 256 possible 8-bit numbers, 2 to the 8th. If you have 10 bits, it's 1024, 2 to the 10th. Well, this is a proof of that. Now, we proved it for 4 bits. We could prove it for 5 bits by, having a task T5, pick bit 4. Number of ways to do that is 2. Total number of ways would be 2 times 2 times 2 times 2 times 2 is 32. But how do I generalize this and show that for m bits, I can have 2 to the m possible m-bit strings? How would I go from this particular proof to one that works for any number bigger than or equal to 1? 2-word answer. Induction, 1-word answer, even better. Yeah, we could use mathematical induction to formalize this. Instead of saying, dot, 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 we could make a proposition that the number of n-bit strings is 2 to the n. And we could prove it for a base case, and then we could simply say, if for n bits you have 2 to the n, how do you get an n plus 1 bit string? Well, we could make that a succession of 2 tasks. Your first task is pick the first n bits, and your second task is pick the last bit. Our mathematical induction hypothesis would say the number of ways to do this first task is 2 to the n, and then the way to bit this most significant bit, we've got 2 of those, so the total number of ways would be 2 to the n times 2. That's 2 to the n plus 1. That proves your inductive hypothesis. Mathematical induction, you can prove this formula for all n bigger than or equal to 1. So anytime you want to say dot, 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 and you want to generalize a process that you can see in your head, you can probably go back and apply mathematical induction and make that rigorous. And counting is a good case of that. Suppose we have a function of 4 input variables. And let's suppose this is a Boolean function. So Engineering 250 again, right? We've got a truth table or something. We've got a function with 4 inputs and some output f. And we can ask how many such functions are possible. In other words, how many different functions of 4 input variables are there? We know there's 16 combinations of 4 bits, but here we're asking, how many functions are there of 4 inputs? And we've seen this formula in Engineering 250. We can write a truth table, and the truth table has 16 rows, 2 to the 4th. That's what we just proved. And the function is completely specified by its truth table. Each function corresponds to a truth table and vice versa. Different functions, different truth tables. So to completely specify a function, all we need to know is what are the values in the output row, output column of this truth table. So specifying a function f of 4 inputs can be done with a succession of 16 tasks. Task 0, choose what the function value will be in this first row. Task 1, choose what the function value will be in this second row. Task 15, choose what the function value will be in this last row. Well, the number of ways that you can do task 0, how many ways can we specify this output value? There's 2 possibilities. We could put in a 0 or a 1. And this second row, how many ways can we fill in that output value? Put in a 0 or a 1. There's 2 ways to do that. And this last row, how many ways can we fill in an output value here? We can put in a 0 or a 1. There's 2 ways to do that. And so the product of these is 2 to the 16th. That's the number of ways we can specify a unique function of 4 inputs. So we have 2 to the 16th possible 4 input functions. And this was a formula we did in 250, where we also noted that this was 2 raised to the n, where n is the number of inputs. And you can get that out of the product rule. This is another way we can get the size of the power set of a set. If you want to construct a subset, all you have to do is go through each element of your set and say, should I include this in the subset or not? So if you have n elements in a set and you want to construct a subset, go through each of those n elements, and your task is to decide whether or not that element goes into the subset. And each of those tasks, there's 2 ways you can do it. You can say, yes, I'm going to include it, or no, I'm not going to include it. And so you have n tasks, each which can be done n ways. And so you have 2 to the n ways to perform that succession of tasks, 2 to the n ways to define a subset. That's why we have 2 to the n subsets in a set with n elements. So that's another version of that power set rule. All right, we have a deck of cards. So deck of cards normally has 52 cards in it, and each card is unique. Has a number and it has a suit. So 5 of diamonds, 7 of hearts, that kind of thing. So 52 unique cards. How many ways can we arrange that deck of 52 cards? In other words, you shuffle it up and you look through it from top to bottom. There's a certain arrangement. How many ways can we do that? Well, the task of arranging the cards in a deck can be broken into a series of subtasks. So T1, choose what the first card is going to be in the deck. T2, choose the second card, and so on. Down to T52, which is to choose the last card. And again, this succession of tasks, when we're done, will result in a particular order of the cards. And any order of cards can be achieved by performing these 52 tasks in a particular way. So the number of unique orderings for the cards in a 52 card deck is the same as the number of ways we can perform these 52 tasks. Alright, well, let's enumerate these. So how many ways can we choose the first card to go into our output deck? Well, we have 52 cards, and they're all sitting in our original deck. We can take any card we want. So there's 52 ways to do this. To choose our second card, we only have 51 cards left to choose from, because we've taken one card out of that and put it in our output pile. So now we have only 51 possibilities for which card we're going to choose for our second. And for N3, there's only going to be 50 possibilities. And when we get down to task 52, there's only going to be one card left. And there's only going to be one way to pick that last card, which is to pick the last card, right? The card that hasn't been picked yet. And so the number of possible decks is just the product of these. So it's 52 times 51 all the way down times 2 times 1. So the product of the first 52 integers. And we have a notation for this, which is 52 factorial, or 52 exclamation mark. So yeah, as someone said a few minutes ago in chat, 52 factorial. Factorials pop up a lot in counting arguments. Anytime that you're multiplying things and each step decreases your number of choices, you're probably going to see a factorial pop up. Yeah, I still have a fruit fly right there. Alright, suppose you have to pick a 6-character password. And each character is an uppercase letter from A through Z. And you want to know how many possible passwords can you pick. Well, 6 tasks. Pick the first letter, second, third, and so on. Right? So N1 is 26. N2 is 26, and so on. N6 is 26. So this is 26 to the 6th possible passwords. But if there's a restriction placed on you, such as you cannot use the same letter more than once, then this starts to look like a factorial again. There's 26 ways to choose the first letter, but now you've only got 25 ways to choose the second. And now you use 2 letters already, so you can do 24 options for the third, 23, 22, 21. So this would be 26 times 25, 24, 23, 22, 21. And there's a shorthand way of writing this. If we were to write this out, multiply it by 1, where I'm writing 1 as 20 factorial divided by 20 factorial. Well, now all of this, that's 26 multiplied through to 21, multiplied by 20 down to 1, all of this is 26 factorial, and this bottom part is 20 factorial. And that's a form we'll see a lot in counting exercises, the quotient of factorials. So 6-character password with no repetition, 26 factorial over 20 factorial. And that's a smaller number than 26 to the 6th. Now what if you weren't allowed to have 2 consecutive letters that were the same, but you could use letters more than once as long as you didn't have 2 letters in a row that were the same? So our first letter, there's 26 ways to choose that, but our second letter, we've only got 25 choices because we can't pick the same letter we just picked. And then for our third letter, how many ways can we pick that? Well, we can pick anything except what we picked for the second letter, so we've got 25 choices for that, and the same for the fourth and the fifth and the sixth. So this would be 25 to the 5th times 26 possible passwords. So all different versions of counting, right? But all just using this one rule, which is the product rule. But it works for a lot of different cases. How many 3-digit numbers can we write if we allow leading zeros? Normally we don't put leading zeros in, but if we consider, 007 to be a 3-digit number, how many 3-digit numbers are there? Well, there's 3 tasks. T1, pick the first digit. T2, pick the second digit. T3, pick the third digit. How many ways can we pick a digit? 10. How many ways can we pick the second digit? 10. How many ways can we pick the third digit? 10. There's 1,000 possible 3-digit numbers. And what are they? They're the numbers from 000 through 999. Well, we know there's 1,000 of those because we're C programmers, and we know if we start indexing from 0, the number of things is that last thing plus 1. So there's 1,000 numbers. But that's another product rule. All right, one more example, and then we'll call it a day, and then on Friday we'll talk about the sum rule. But let's talk about functions. So let f be a function or a mapping from m to n. And let's suppose the number of elements in m is little m, and the number of elements in n is little n. So these are finite sets. Okay, how many functions, how many possible functions f are there? How many different functions from a set m to a set n with these cardinalities? Well, remember, to define a function, there's lots of ways to define functions. One way to define a function is for each value in the domain, show what the function value is. So defining this function, right, we're asking how many ways can we create such a function. The number of ways to do that is findable from the product rules. So let's break this task of defining a function into a series of subtasks. So let's set a task T1, choose the value of f of m1. So I'm going to think of this set, which has a bunch of elements in it. I'm going to think of this first element as m1, the second element as m2, and so on, and the last element is m sub m. So I have a series of elements that I'm mapping from, and my definition of f is based on the following subtasks. First, choose what value this first element maps to. Task 2, choose the value of f of our second element. task 3, choose the value of f of our third element, and so on up through task M, which is choose the value of the last element in M. All right, how many ways can we do task 1? We have to choose what value M1 is going to map to. Well, we're mapping into this set N, and N has little n elements. We could set f of this number to be equal to any of those n elements. So there are n ways to make this assignment. And if there's no restrictions on the function, there's n ways to define f of M2 and n ways to define f of M3 and so on. And so the total number of possible functions is n multiplied by itself m times. That's n to the m. This is a generalized version of what we did a little while ago when we looked at the number of Boolean functions. Because with a Boolean function, we're mapping into a set with two elements, 0 and 1. So our little n is equal to 2, and the number of possible functions is just 2 to the m, where m is the number of input variables. Or sorry, the number of values that we can map from. So 2 to the number of variables. All right, if instead we put some restrictions on our function, like suppose our function has to be injective. So an injective function, we can't have two different values mapping to the same thing. So with an injective function, t1, we could still choose any of n values to map that to. But once we've chosen a value for f of m1, we can't choose that value again for f of m2. So here we would have n minus 1 options and n minus 2 and so on, all the way down to n minus m minus 1. And so we'd get something that looks more like a factorial divided by some other factorial. Okay, so these are just examples. The specifics aren't as critical as the general idea of the product rule. And it's just the same thing. Take the number of ways you can do a task. Each task in a succession of tasks, multiply those together. That's the number of ways to do the equivalent task. All right, so we'll talk about a different version of this on Friday, which is the sum rule. And the sum rule will relate to a different way of breaking down a procedure into a series of tasks. And then we'll put those together and we'll build on from there. All right, thanks. I will see you next time. Have a good afternoon.